Okay, here we go. Um, okay. In theory, we're live. I I don't know why I always say that. I don't trust technology. I don't know why, but I just don't. Um, so where are you located? You're in Madison?
I'm in Madison, Wisconsin,
Yeah.
United States.
I've been there one time. Drove through Madison on my way to Milwaukee. I think that's how it works, right? Yeah,
Yes,
yeah.
it's Milwaukee is only an hour away from Madison, so
Yeah. There was a
you're in the bigger
convention.
city.
Yeah, there was a convention in Milwaukee that we went to and drove through Madison. Madison was really great. I really liked it. Um, all right, I think we're ready. So who are you and what do you do?
Yes, so my name is Elena D'Onghia. I'm an Italian American scientist and located in Madison because I'm associate professor at the University of Wisconsin Madison. I have a background. I grew up in Italy, and I also traveled in Europe before coming to US, and have a training in physics. But with my PhD and my later research, I became actually mostly an astronomer in the last few years. And now I work in between galactic dynamics, which is my passion for pure research, which is more related to math and physics but applied to astronomy, and now aerospace, which is my second passion because I want to serve the society with an application, with in doing something using creativity and using my background in physics to see if I can be useful for the next few years to society.
Well, I would love to talk about that, but like, and I'm really interested in the NIAC project. That's how you came to my attention. Was you were one of the winners of a recent NIAC grant about a topic to build an artificial magnetosphere, and I'm really excited about that. But I'm also a gigantic fan of the Gaia Space Telescope, of galactic dynamics, of stellar motion, and all of the amazing mysteries. So I want to talk about that first before we shift over and just to sort of give people a better background of what you work with. So you lead a team at Madison working on the galaxy. Can you talk about that?
Yes, absolutely. Yes, I have a team of young students. They are graduate students, so they are doing their own PhD, but I also work with undergraduate students. And the common theme is try to understand how our Milky Way came together, and also, how the stars move in our Milky Way. The reason for that is that we are really in a period of renaissance for galactic dynamics. So, in order to understand the motion of stars, and the reason is exactly because we have data coming up from mainly from Gaia, the Gaia mission, which is a satellite, it's a telescope orbiting around the Earth. It's actually in space around us, and it's taking images of the sky every day. And with these images on the sky, it's giving us information for 2 billion stars in our Milky Way, 2 billion
That's
stars,
so many stars. That's
about
crazy.
their motion, their location, and their distance. Now, this is a big problem in astronomy. It's been a huge problem because in astronomy, we see the sky. We can see with telescopes, deep in space. That means we go back in time, watching, the sky, but we don't know. We never know exactly the distances. So, and for the Milky Way, until 20 years ago, with the previous mission, which was Hipparcos, we knew the motion of a few thousand stars. And before that, the information came from Newton, so from 400, 500 years ago,
Right, the person.
the person.
Yeah.
So we had a gap of 500 years. Then came Hipparcos 20 years ago and gave us some little information. And, that opened the eyes for a few thousand stars. And now comes Gaia and brings the information for 2 billion stars. So this means that we are in the renaissance for astronomy, because we can know now, we can, discover how far are stars, how do they move including our sun. And for example, we can know also what is the structure of our galaxy. We know that our galaxy is a disk, so it has a disk of stars, and there are features like arms, probably similar to other galaxies, but because we are inside our own galaxy, we are not sure about that. So we are discovering, like blinded people now with the data, trying to figure out, what is the structure of our galaxy? How does it look like? And I think Gaia is giving us also a lot of information about this, and a lot of information about also the motion of stars. For example, we are discovering that our sun did not form here where we are now, but it formed elsewhere. And our sun moved away from its initial location. And it moved away because of resonances. So because the sun, has been pushed away by, by the presence of these features in the galaxy, like spiral arms and a bar at the center that's rotating with the galaxy, are all features made by stars. They are like a pattern, like, waves, and they are perturbing the stars in a way that they move, in going in, like in a dance with other stars, because they resonate in their motion with other stars. So we are in the process with Gaia in the next 10 years to know exactly which stars resonate with other stars, what is their movement, their motions, and the structure of our own galaxy.
That's really interesting. I mean, I know, like, we think about resonances like Jupiter, with the moons of Jupiter and how the different moons are in various resonances with each other. But for the stars in the Milky Way to be in these kinds of resonances, that's something that I didn't expect. What else has Gaia taught us about the Milky Way in just a decade now that we didn't know before we started this process?
So he told us that mainly that there are a lot of, so we thought before Gaia that the stellar disk is quite quiescent, quite smooth. And with Gaia, we are actually opening our eyes and seeing already that around our sun, the disk is not smooth. That means that stars are, they are forming aggregations, associations. So they associate, not because they are formed together, but because they resonate, for resonances. Mm-hmm. So we are discovering resonances. These resonances are due to really the structure of our disk. And we are discovering that there's a lot of perturbation, like undulation in our galaxy, corrugations, and the disk is like, it's plenty of waves of stars. It's a little bit like in the ocean, the stars move like when you float in the ocean, and, a pattern comes and you move with the water. It's exactly what stars do. A pattern comes and they undulate, they basically move around. And we're discovering that there's a lot of these patterns that we didn't know about. And we are trying to figure out what causes these waves. Like in the ocean, the ocean has waves when something perturbs it. And in the Milky Way, there's a lot of perturbation. So what we are discovering is that eventually there are a lot of probably clumps of dark matter. They might perturb the disk. This dark matter is not visible. It's just making, 30% of the budget of the universe mass. We are only making 4% with planets and galaxies. And eventually it's perturbing the disk, and also visible galaxies, like little dwarf galaxies. They are our companion. They are small. They orbit around the Milky Way, and they might perturb, our vicinity. There's one dwarf galaxy, especially called Sagittarius, that it's eventually perturbing and creating a lot of this corrugation. Also, with Gaia, we discovered that Milky Way cannibalized another small galaxy by gravity. gravity is the most important force in the universe. So it's what really regulates in the universe, the motion of everything. And so by cannibalization, the Milky Way probably 9 billion years ago cannibalized a smaller, another little galaxy that at that time was big enough that it's still now in the middle of our stellar disk. So they're seeing the remnants of that cannibalization. And I think this is another big story, another big discovery that came with Gaia.
So this idea about dark matter, the presence of dark matter within the galaxy itself, when I envision dark matter, I think of this sort of smooth halo, a big blob that the Milky Way is embedded within, and this dark matter halo is what is responsible for the overall motion and cohesion of the Milky Way. But could you, if dark matter was in smaller blobs that were floating around, is that something that you could see in the motions of the stars?
Yes. So indeed, when so initially people thought that dark matter is maybe like a cocoon. It's like a smooth cocoon that surrounds. It's like a halo, around the galaxy, and it's making 90% of the mass of the galaxy, just 90%. So it's the majority of the mass, but it's like a cocoon, extended, and the visible galaxy will be at the center of this cocoon. In reality, when people made the first numerical experiments to really simulate the dark matter that we believe is the framework of our universe, they realized that it's not smooth, it's not a smooth cocoon, but it's clumpy. So it's made of clumps of any mass. So the little clumps are, they have random orbits. So they are, orbiting around the center of the galaxy, or orbiting around, the central part, which is the visible galaxy. And then, that's what this is a source of perturbation. And this perturbation could actually perturb the motion of the stars, because stars and dark matter, they feel gravity both. So gravity is affecting both. And so one of the new research areas that came up in the last few years when these numerical experiments became available to the community is that, there might be these clumps of dark matter. They are perturbing streams of stars that we see on the sky. So we have also streams in there's a halo of stars as well around our galaxy. And these streams of stars can be perturbed by the presence of these dark clumps. So an interesting research area is studying the motion of the stars with Gaia in order to understand, or with future missions, in order to understand if we can constrain the nature of the dark matter, which is a mystery.
Yeah. I mean, we know it's there, and we're getting better at mapping it, and we can use it as a telescope to be able to view, to use gravitational lensing, but we still don't know what it is.
Exactly.
Right. Well, one idea is that dark matter could be, say, these primordial black holes, these black holes left over from the formation of the universe. Would a compact object like a black hole provide a different motion of the stars than a larger diffuse blob? Could you get to a point where you actually know how big these chunks of dark matter are?
So people look at into compact objects, including black hole. It seems that there's no enough of those objects to really make up all the mass of the Milky Way dark matter.
Right. Okay.
So you really need to invoke some exotic, particle that has never been discovered. And so it is really the mystery. And it's quite an embarrassing time right now, because I think it's more than 30 years that we have a framework, a cosmological framework for dark matter. We have all the paradigm, to form structure formations, to form galaxies within that framework. but physicists did not discover the particle yet.
Well, I wouldn't
So
call it embarrassing. I would call it interesting, exciting,
interesting,
right? Like,
exciting, but
yeah. I mean, like, what's life without mysteries? So,
well, it could be that because the dark matter is elusive in some way because it only interacts with visible matter by gravity, but does not interact eventually in any other way. So it's difficult to be detected.
right.
However, we have as scientists, we have to keep always our mind open that there might be something else that we just don't know, and we might be on the wrong track.
Yeah. Well, I mean, with science, you try to test every idea that you can think of, hoping to disprove them, and it's only the ones that you just can't disprove that just keep sticking around. That's what turns into the consensus that maybe it's right, but still anyone can disprove it at any time. Um, so I'd like to talk a bit about like the history of the sun. Like the sun probably formed in a stellar nebula with a bunch of other stars 4 billion years, 4.5 billion years ago. Do we have any sense of where we started and who our siblings were at the time?
This is a very good question. So we don't have a conclusive answer to that, but thanks to Gaia and thanks to the next upcoming survey, we're actually thinking that the sun has different properties of the neighboring stars, and so it probably formed in a cluster, so with other siblings, but eventually has been dispersed and moved away. So it's an immigrant in the part of the galaxy where we are. So it doesn't belong to. We don't belong to this area. I feel like myself, I'm an immigrant in United States, but so the sun has been immigrated, migrated from another area, and eventually it's probably has been also, a few kiloparsecs, so several, light years, thousands of light years away, and it might have been, a slow process, the one of migrating. So, and it's really due. This is the innovative part that we believe now, due to resonances. It might have just resonated with some of these non-axis symmetry features. We call them like this, like spiral arms, to just migrate where it is now. And we know it because the sun is really placed almost in the midplane in our galaxy. And that's where basically the majority of the stars that have peculiar properties like our sun do reside if they migrate. And we know this because we make models. We use supercomputers to make models to see by gravity how stars move, just mocking exactly what happens in the Milky Way. So we have that level of details right now in our models. So it's not like the time of Newton or where people use only linear theory or pen and paper or very detailed calculation. But now these days we can really using numerical experiments to capture the complexity of gravity and see really how several stars move together by collective motions. So very similarly to what we believe is the physical process that regulates the motion of the stars, and we can compare to what we are learning from Gaia and from these new surveys that is telling us what the nature does.
And like, I mean, this idea, I guess, of these interactions between these stars, just one by one plucking the stars out of the stellar nebula until the whole thing is sort of spread out. Do we think that we shifted from, like, did we start at the same, at least, distance from the center of the Milky Way? Did we perhaps start closer in, farther out? Is there anything weird about the sun that says that maybe it came from a very different part of the galaxy?
It will not come from the central part of the galaxy. So it might have been either slightly inner part than we are now, or slightly outer or where we are now, just a few kiloparsec away, but not from the inner parts. And it takes a while, before it really moves its motion. But this is exactly the frontier, right? Right now, it's the forefront frontier, for research about galactic dynamics. The ideal, let's say the ideal scenario is that we want to learn about each star. Where does it come from? That's the big question.
Right.
Yeah.
So you could roll the whole Milky Way up back in time.
Mapping.
And pull every galaxy that merged in and go right back to the beginning. That would be... Do you think something like that is possible? Do you think you could get to a point where you could... I think about, say, a three-body interaction is so chaotic, it would be really difficult to unravel the history of three objects interacting. We've got 100 billion objects interacting in the Milky Way. Do you think we could get to a point where we could start to unravel how the Milky Way came together?
I think we are not there yet, but with the information that we get, not only from Gaia gives us distances of stars and gives us the motion. So it tells us, how they're moving. But other surveys like the Sloan survey, the SDSS-5 is called, gives us metallicity information, gives us the composition of those stars. And the composition tells us a lot, because stars that are born together, siblings, do have the same chemistry. So they have their ID with chemistry. And then they get dispersed in the Milky Way because of tidal interactions, gravity mainly. They get dispersed. But they keep, just tagging their metallicity. I think, comparing that they might have similar metallicity, but also similar velocity when they're born together. So keeping all this information together, then the idea is to try to tag all those stars and looking for the siblings, which are the stars that have similar ID in chemistry and similar velocities.
Right.
So that's a big frontier now.
Is there a galactic chemistry? Could you tell when some dwarf galaxy was consumed by the Milky Way? Do all of those stars have any kind of similar chemistry? Or is that information lost?
So the stars that are coming, they have an extragalactic origin. That means that they are not born in situ. They're not born in our disk by gas, but they are born elsewhere, and they've been accreted by cannibalization. They usually have they are more poor in metals. So they are more poor. So yes, we have some way to distinguish them. And they might have also different velocities because they are coming from something that has been accreted. So those things, we're not there yet, but there are already progress done with Gaia and the combination with these other surveys about metallicity. So we already know some cannibalization that happened, also of small little dwarf. But what we'll learn soon, also combining the new models that we have, the new computational power that we can use these days, where, as you said, you overcome the problem of the three body because you can study n body. N can be, as many as a billion stars, and solving the equation of motion for a billion of stars with supercomputers. Basically, you don't have to do it pen and paper, so that you're not able to do it. But using these complex codes, you can actually follow the motion of all those stars and stars by gravity and capturing all their features by gravity. So basically, you are overcoming that problem these days. That's why it's really a challenging but also very exciting time, because we have more models, more computational power, and now more data that opens our eyes, in our galaxy that we didn't have before. So we are making really a step forward after 500 years.
Right. Yeah. Yeah. Newton would be glad to see the work that's being done. I got one last question about galaxies, and then I'd like to shift gears. Where do globular clusters come from?
Oh, this is a $1 million question. I think there's no real consensus about. So these globular clusters are very interesting because they are dense structures of stars, but we know that there's no dark matter there. So there's no, and so they are an example of structure where dark matter does not surround them. So the consensus that isn't there is because the debate is because some scientists believe that they had dark matter, and this dark matter has been stripped by gravity, because usually dark matter is more extended than the stars. When the stars are more concentrated in the inner parts in any structure, and then the dark matter is like a surrounding area. So they've been stripped because it's more susceptible to tidal torques and to gravity. And other scientists don't feel that this is actually the explanation. And so those globular clusters just formed by a big burst of star formation from initial clouds of gas. But there's no consensus. It's very difficult to find structures so dense, even when you start from an initial cloud of gas. So there's a lot of physics there that involves the formation of globular clusters. And unfortunately, the numerical simulations in this case, in a cosmological context, when you really want to form globular clusters, when you form the galaxies, in those very complex simulations, it's very difficult to resolve those structures. And so it's hard to learn about really their origin. So there's a lot of debate, but this is one of the most interesting questions, because globular clusters are a mystery still, their origin, but they're very common. So all galaxies have globular clusters. But the interesting part is that they are very old structure. They can be almost as old as the universe. So they're there since a long time. Mm-hmm. Our galaxy came together much later than the globular clusters. Probably the globular clusters have been formed elsewhere, or they have been formed at the beginning of our galaxy. And they are the witness of the early universe, and they're around us. So they contain the oldest stars that we know from the universe.
So what's a weird idea about globular clusters that you like?
I'm not a fan of the idea that they are formed, that they had initially a dark matter subhalo, a cocoon. So I think they are really, I think they might have been formed when big concentrations of gas, were in the galaxy in the past. Maybe they've even been formed in initial disk, like giant molecular clouds when you form stars in the mm-hmm. disk, in a primordial disk, and then they might have been stripped away once they're formed, and along tails, because we know that galaxies go through interactions and distortions with other galaxies because they interact all the time, and they might have been later on accreted, in other systems or in our Milky Way. So they might have formed a long time ago in some seeds, initial seeds. And
could they have formed before the galaxies, do you think?
They formed definitely before the galaxy.
Huh.
They formed definitely before the galaxy.
So was it possible that there was the way the density of the universe was, or the temperature, or the particle environment, or whatever it was, that this was the preferred structure, was these weird spheres, and then later on, as more material was flowing in and there was more tidal streams, then you got these things spinning, and that's when you started to get the larger galaxies.
Yeah, I would think that would make sense to me. It's difficult to prove it because we don't have computational power, or we are getting to the point now, but not yet, to really give an answer to that. But definitely they formed much before the galaxy, because in our understanding of the universe, and this has some, has been proved by observations. When you look at deeper in space and you see basically back in time systems are smaller in the early universe, and they become bigger by time. So today galaxies are, they grew up. They were much smaller in the past. So the little things, so little dwarf galaxy, little globular clusters, all things that have low mass and size, they formed a long time ago. They're old. And things that are, bigger, they just form later on by accretion, because gravity tends to put together mass and growing by time. So earlier you go, more, globular clusters are also very old, because if you look at the age of the stars, they have been formed a long time ago. They can be, 11 billion years old, 12 billion years old. So almost like the time of the universe.
Yeah, it's I find them really fascinating, and one is because they're very easy to see with a pair of binoculars or a small telescope. You can just see them right there in the sky, like the M13 in Hercules and things like that. And so you've got this just incredible, beautiful, and the better the camera, the better the picture, the more stars there are, the more this just looks like this incredible object. And yet we still just kind of don't know where they come from, and it's great. I love it. Maybe I hope we never find out. All right, now I want to shift gears, and this is going to be like an extreme gear shift to go completely in a totally different direction. As the listeners know, I'm a huge fan of NASA's Advanced Innovative Concepts, the NIAC Awards, and these are these small grants that are handed out to researchers who are trying to solve some interesting, fundamental, very out-of-the-box idea for space flight, for astronomy, for science, for Earth observation, for any of these ideas, but like only weird ideas, only extreme ideas are what's interesting to this group. You recently were awarded one of these NIAC grants. So tell me, what is the concept that NASA is helping you try to investigate?
So NASA awarded our team. So I'm the PI, but I'm part of a team. So the other people, that contributed to this, and awarded this idea because we came up with a novel idea about how to shield the spaceships really, from cosmic radiation. And the reason is because, companies, also private companies like SpaceX or other companies, they are really pushing for, with the idea, and are engaging the audience and the public with the idea that we'll go to Mars, and, we're going to explore other planets with the human exploration. But they never say really that this is actually not possible these days. We can only go to the moon for a short time, but, landing on the moon and staying for a long time, and, really having astronauts with moon habitats right now, it's not possible because there is cosmic radiation. So space is actually a killer, So as humans, we are very privileged on the Earth because the Earth has a magnetic field due to the interior of the Earth. This magnetic field shields away naturally for us all these harmful particles for our body. Once we go outside the Earth and we start going on the moon, but even more if we go to Mars, which is more far away than the moon, so we need to travel there 6 months to go there. So we are exposed to all this harmful radiation. That's a little bit like being exposed to radiotherapy, like when you have cancer. So it's actually destroying your tissues. So the human species is actually very fragile to cosmic radiation. These are very energetic particles like protons or ions, or heavy ions, and they are accelerated. They're indeed called cosmic rays. They go very, very fast, and passing through our tissues, they are actually depositing a lot of energy, and this can eventually making humans very fragile to cardiovascular problems, damage of the brain, maybe developing cancer. So we don't know exactly what are all the issues with that, but definitely NASA is aware of this problem. And so we came up with the idea of looking at the nature and trying to see how nature makes it to preserve life on our planet. It has a magnetic field. So no, we were not the first one who came up with this idea. People have looked at that, but I think that the advantage we had is that we are reproposing the idea of a magnetic field around spacecrafts, but with using the new technology like superconductors and using a new idea for a new configuration for the magnetic field that hasn't been used before. So our magnetosphere has been, awarded by NASA because they found novel that we have a deployable device. We provided, we invented some way a deployable device, which, it's something that NASA feels that would be the way to go. And also the geometry that we proposed produces a magnetic field in the outer part of the spacecraft, but does not provide any magnetic field in the inner parts of the spacecraft, where the astronauts would be basically based. And this is also something that hasn't been proposed before. So the previous magnetic fields were much more confined around the spacecraft, and this can cause troubles because cosmic rays, once they impact the spacecraft, they basically generate a shower of other particles that can be harmful, like neutrons, to our to astronauts. So we reduced that problem, and I think NASA wanted to bet on this and give us, awarded us with phase 1. That means that we have a feasibility study to show the proof of concept and see if we can move on with the next step.
Yeah, I've done a few articles and even videos on this concept, and you can go back in NASA literature to the 50s, to the 60s. People have been proposing this idea. There have been other NIAC awards in the past that have attempted to investigate this. The European Space Agency has awarded some projects to do this out of Italy, I think. Everyone puts comments in my videos saying, why don't they just build a magnetosphere like the Earth? It's really hard. So can you sort of explain why this is such a difficult challenge? What kinds of forces and energies are we dealing with that is making this so tricky?
So you need to create a magnetic field which has to be quite extended outside the spacecraft, because you want that this magnetic field deflects the cosmic rays coming from space. On the other hand, you need to, the real challenge has been always the current of each coil that generates the magnetosphere, and to how to sustain that current. And you need to have a high a lot of current and a high magnetic field to really deflect the majority of these energetic particles. This creates also big forces, magnetic forces, and you need to have a robust, solid structure. Solid structure means that the weight is large. Mm-hmm. And so this is the big challenge. So how you balance, you need to have something light, because, you can't bring in space to weight. This was the problem that people had in the past. 10 years ago, there was a successful really idea that came from Europe, especially from an Italian team. And they proposed really an active shielding, which is a magnetosphere. But the weight of the superconductors at the time, before the new era of superconductors or new materials that are coming up now, made them the structure too heavy and unfeasible. So they also proposed a geometry for the magnetic field that was too close, was too confined to the spacecraft. So they really learned the lesson, and which we started from learning from them, that was not the right geometry to use. And so we changed direction. So we used basically the previous ideas.
Right.
We made we learned from that, and we moved. I think we are proposing at the time when active shielding is much more promising now, because new geometries and because new materials and new superconductors that will probably allow to make this eventually feasible.
Right. Yeah, the the understanding that I had gotten is up until this point, every idea is in terms of mass and in terms of the power required to generate the electric field as well as the additional material, you're better off just surrounding your spacecraft with metal, or right, that in the end just metal is more cost effective than any kind of magnetic field that we're able to generate. So you are pretty excited that there's new technology, there's some new ideas. So let's talk about some of the new technologies that have come together that you think are going to enable this.
Right. So let's say the new game change now is the superconductors of new generation. For example, we suggested the REPCO, but we haven't done yet a complete feasibility study. Okay, this is just what we were thinking about to suggest. REPCO are now, these superconductors are like tapes. So they are very small, and you tape them around the coil. So you have to compute how many wrapping you have to do on each coil to generate the current that you need. But they use little current each, for each wrapping. So you can sum up to the current that, for example, we needed, which is a few million ampere for each coil. So it is possible to do these days. These were not available 10 years ago. And they also work on a different temperature than what was supposed in the past. So now they have, they have a higher temperature. So they basically, they are much more suitable for, in terms of weight and in terms of feasibility for studies like this. And they were not on the table 10 years ago. So I guess the combination of this with, we also made the initial calculation of how many coils we would need in our configuration to generate. And we found that there are 8 coils for now, but we can optimize better now with the NIAC, with these funds, because we want to really, you have to find the balance between reducing the weight as much as possible. So you want to, possibly find an optimization between the number of coils, possibly as lower as possible, because they have their weight, each of them. On the other hand, they need to be, you need to create enough current to generate these magnetic fields, and they need to be solid enough, that you can basically bring them in space, and keep their they can contrast the high magnetic forces, which will try to destabilize them once the magnetic field is acting. So we found that, I would say what we need to reduce the weight as well. So it's a little bit too heavy right now, but it's much lighter than any other, we compared already any other idea that has been proposed. That's why, NASA bet on us. And, but, we have 9 months now to optimize our model and see what we can propose for the next step as a feasible study. Also, let me tell you that, I'm the PI and the principal investigator because I initiated this by my personal, curiosity, and also my will to serve this community in something that was a big challenge. But I have an excellent team of another physicist, Paolo Desiati, who is a high energy physicist, and he really he knows a lot about magnetic fields and cosmic rays. So we came up with an initial concept, and then we had fabulous undergraduate students in mechanical engineering and physical engineering who actually did the structure. They really designed, how we should put the coil. And so this is really a team of students, young students, and basically two more senior people like me and Paolo.
So let's imagine that, we're 30 years in the future. You've gone through all of the process, and there's prototypes, and now there's a new spacecraft that's being launched for the first time. Maybe it's a mission to Mars, and they're going to deploy the radiation shield. So what would happen? Imagine NASA, they're in space. They've just, they've done their boost and they're on their way to Mars, and NASA gives them the order to deploy the shield. What would happen?
I think what will happen is that right now we made calculations to reduce, the cosmic rays impact of almost 40 or 50% for the ones that have lower energy. And what we want to do is now to improve, to go to higher energy and see how much we can basically reduce that flux of cosmic rays. But in principle, if this is feasible, this means that we will now reduce, to zero the impact of cosmic rays. But this will mean that, astronauts will be able to absorb less radiation during a trip to Mars. So this will mean that they will probably develop later, bad response from the body to cosmic radiation. So it will preserve some way life. And this active shielding is going to be then, if you find this interesting for spacecrafts, we have to combine with the new design that people will do for the habitats, for the moon or for. So it has to be combined with the passive shielding of materials that people are trying to use now to preserve the habitats from cosmic radiation, but they are not as effective as a magnetic field. I think the future is to find ideas that could be combined, passive and active shielding with the magnetosphere around, materials that help to preserve from cosmic radiation, to actually allow astronauts and human exploration to stay on the surface of a planet. Otherwise, we have to go, we have to go in the inner parts of the planet. I mean, below the surface.
But I guess, like, I'm imagining, like, physically, like, you've got this spacecraft, and you say that what's key to your idea is that it's deployable. So would, like, these torus, I don't know, magnetic field emanators to sort of come out of the spacecraft? Like what would it actually look like if we could see it deploying the shield?
So it will be deployed a few meters away from, it will start very compact around the spacecraft, and then it will deploy, and then it will remain fixed. And then, in space, will generate this magnetic field, and the astronauts will not feel it. They won't feel anything. They will just absorb less radiation. So
how far away would it be?
I think our calculations proposes 5 meters away. We haven't optimized it yet.
Right.
But
yeah. No, for sure.
That size.
So 5 meters away, and then and you say that right now your calculations are that there are 8 of these booms. Are you giving them a name? But anyway, but that are sort of around the spacecraft, and then these booms or magnetic field arrays will then generate this magnetic field, and they'll overlap each other around the spacecraft. Is that?
So each coil, so the structure of the coils will be deployed, and then the coils will start, generating, they will have the current inside each coil. This will generate magnetic field, magnetosphere, and it will be outside that 5 meters. So basically, that will be the region where the magnetic fields will be active, and inside the 5 meters where has been deployed the device, there will be no magnetic field. And so that's the idea.
Where will the particles go? Will you be like here on Earth? The Earth directs them to the North Pole, and we get beautiful auroras. Where would you be directing the particles?
So our magnetic field is not a dipole. So it's not like the one of the Earth. It's a different configuration. So they will be deflected. Let's say this is an orbit. It will be deflected like this, like this, like this, like this. So they will arrive, from everywhere and being deflected away. So they will come closer to the spacecraft, but then being deflected.
Right.
A percentage will still penetrate because it won't be an efficiency of 100%. But but the idea is to reduce and maybe later on to improve. So.
And what kind of power requirements do you think this is going to need?
So the power, we made very preliminary calculations, but it's not going to be too high. I think it probably is 100 watts or something like that. So it's going to be, starting, it's not a huge.
700 watts. Is that what you said? Yeah. Oh, that's not that bad
It's
at
always
all.
feasible, but it's not a final calculation.
Right.
The current of each coil is a few million ampere, and we are trying to see if we can optimize that too. But if we can, power it, then with the superconductors, they will keep working in space, and so I think this is not a big problem. The big problem we have right now is actually reducing the weight because 8 coils, it's almost 3 tons each coil, so it's 24 tons,
Each coil is 3 tons.
3 tons. So we have to reduce it, but we haven't optimized the materials.
Three tons would give you a lot of metal.
Give you a lot of metal, but I mean, the
Yeah.
previous models were, I don't know, 300 tons.
Yeah. Yeah.
They
I
were
think
really,
the launch capacity of a starship is like 150 tons to
exactly.
low Earth orbit.
Yeah, I
So
mean, we
there'll be
need to
lots of room.
reduce. We
Yeah.
need to reduce it, and we need to work on on new materials as well. So we haven't optimized that part yet, but this is the big challenge
Yeah.
now to try to think about how to do that. And also for us, next challenges would be interesting to test on space, maybe on the International Space Station, one of these coils and see one of these configuration,
Mm. Um,
to see really
and then
what
do
if
you
it works.
see, I mean, it sounds like, attempting to shield in all directions what on a spacecraft where mass is everything. Does this application make more sense on permanent stations, like say on the moon or on Mars?
I think this configuration has been, so the devices say the design of the structure here that we propose for the NIAC is really for a spacecraft, but we know that, even spacecrafts are in evolution. So, and we know that for the Artemis project, they are not going to use active shielding. They're going to use vests or, something like passive shielding for astronauts. So, but well, it needs to be, integrated with a good design depending on the habitats that you want to build up on the moon. I think this is the next challenge. So once active shielding becomes again it becomes there are new interesting ideas coming up. I think these two areas have to integrate the designing for moon for moon habitats, moon village that people are thinking now, and the active shielding have to be integrated. Probably they will have a different design depending, but the idea now is to propose new geometries for the magnetic field, and and showing that the numbers are there to build them up, and then of course the integration for the design will be probably changing depending on the habitats that people are thinking about, or they have to integrate it in order to have the maximal optimization between
Right.
how to create an habitat on the moon. And if these things will work on the moon, eventually become good ideas for Mars. Once I think we are not there yet, so
Does
Mars
it
is still far away.
Do you think that it will become more efficient and effective at a larger scale? Like if you wanted a version that would protect a large space station as opposed to protecting a small spacecraft. I mean, I'm sort of imagining the 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 mass of these coils. Each one is like almost the mass of your entire spacecraft. But if you make a space station that is 100 meters across, do things become a lot more efficient as you scale up?
So for the space station, really for the like ISS, I don't think you really need to build an active shielding necessarily because they well for now
Well, they're
if you
protected
cannot
already, but
yeah exactly. So but if I think there's no to bring them on the moon, you can make use of the 3D printers. So I think some of the stuff can be printed there, or we have to not necessarily you have to to transfer all the material in one launch, or so one has to think about how to do it. But I think that I don't see a big problem in building up structures that contains a lot of coil. I think the clever we have to be, or people have to be when they build up the structure, is really to build up something that is well integrated in the structure, and but once they will start building up stuff like this, I think that would be one can think about clever ways these days to basically build them up even in larger structure. They can have different, configurations and
Yeah.
on a moon, on a habitat instead of the spacecraft, which is more confined in a small system.
So what is your sort of motivation with this? It's very rare to see an astronomer who wants to get so involved in space exploration. Mostly they see space exploration as taking away their budget. But so what fascinates you about this idea of human space exploration?
So I had a very bad health problem 5 years ago, 4 years ago, actually, almost five. And so I had a bad problem in a relatively younger age. I felt that life can be short. And so although I was fascinated by the idea of contributing, to society with the knowledge of stars, I thought that I needed to do something more related to space, but more applicable. And so I was very much intrigued by what Elon Musk was doing. And I thought, how can I contribute, with my knowledge? And with Paolo, we are good friends. We start thinking about, okay, how about the shielding? Because we know as physicists that cosmic rays are harmful. And so we thought that we could come up with ideas. And we actually realized there were not many people working on this. And so we started working. So after 3 years of hard work, finally, NIAC has been awarded to our team, and so I'm actually I'm very happy about.
It feels. I mean, when you think about it, it sort of feels like Star Trek. Like, put up the shields. That's the hope, right? Is it like all of these pieces that Star Trek and other science fiction has taught us will happen in the future. We need them to come true, and I guess it's bit by bit. This is how we do it. If it's fascinating work, and good luck with the research. Now comes the hard part, where you actually have to prove all these ideas and deliver your report to NASA. What's the best way for people to keep track of the project and see how you're doing?
I think we will create probably a web page soon, and definitely we have been invited. We have been invited to some conferences, and we will probably post something online. So I will keep you posted if you're
Perfect.
interested. Now for the next 9 months, we have to work hard, but
Yeah.
we will keep going.
Well,
and so definitely.
Well, here's to winning a phase 2. That's when you know you're really onto something, when they keep the project going. Well, Elena, thank you so much for taking the time to chat with me today. Absolutely fascinating work, both in galaxies and space exploration. I appreciate you taking the time, and and good luck.
Thank you so much. It
All
was a
right.
big pleasure, a great pleasure for me
All
as
right.
well.
Take care.
See you. Bye bye.